Today, we're at Bletchley Park in honor of Alan Turing's 100th birthday. Bletchley Park, just north of London and between Cambridge and Oxford, was considered by many as the birthplace of modern computer science.
In 1938, again in anticipation of war, the government code and cipher school, and in the main, their operational director, a gentleman called Alistair Dennison, had drawn up a list. He had sent two people out to troll through the people at Oxford and primarily Cambridge and to some extent Oxford, and drew up a list of people who they approached who agreed in the event of war would report immediately to Bletchley Park. Britain declared war on September 3rd, 1939. The following day, September 4th, Turing and several others reported to Bletchley Park. As the requirement for more people was needed, some, predominantly a gentleman called Gordon Welchman, he had been on the initial list. He'd arrived the same day as Turing. He went back to Cambridge and he started recruiting all his best students, and in effect what they created here was the world's first skunk works, a secret innovative organization where there were no rules. Eventually their main benefactor became the Prime Minister, Winston Churchill, and they persuaded Churchill that this place needed more resources. Churchill agreed, and he wrote a famous a letter was written by Welchman, Turing, and the two deputies to Churchill, and one other number, a gentleman called Stuart Milner Barry, actually delivered it in person to Downing Street. Churchill amazingly read the letter the same day it was delivered. He put a famous "Action this day" stamp on it with a handwritten note to his chief of staff, a chap called General Lismay, which said, "Expedite with extreme priority and report to me when it is done." And really from that point, September 1941, Bletchley Park got all the resources they needed. They threw, in effect, the smartest people together in Britain and said, here's the budget, this is the end game, and that's why they invented some of these technologies, which probably wouldn't have been invented for years.
In many ways, Bletchley Park was an early version of a multidisciplinary science center, much like CERN or NCSA is today. Many brilliant people with different skills and backgrounds were brought together to solve difficult problems. The combination of the skills and collaborative environment resulted not in just solving the problems of cryptography that they were facing, but in addition solved broader problems for all of computing and all of society.
When the people arrived here, they knew when they arrived that the Germans had taken a machine, a machine which we tend to call Enigma. Enigma was a particular variant of an encryption machine. That machine was modified from the commercial version, and it allowed them to encrypt messages. This was going to become a machine to be used for operational communications. Very short, 200, 250 character messages. Hitler had conceived, and his generals, a type of warfare never seen before, which became known as Blitzkrieg. Very fast movement, 50 miles a day, particularly when they invaded France and the latter stages of their invasion of Poland. You couldn't use fixed line communications. You needed to use wireless communications. Here was a device which was portable, weighed 25 pounds, ran off a battery. You could encrypt messages, and then as a separate process, they could be sent using the fairly new technology of wireless radio. It was the Poles who were the first to recognize that the age of machine cryptography had arrived, and the sort of people who would be good at dealing with it were mathematicians. In fact, they even went so far as to put on a course in cryptography at the University of Poznan, invited 20 or 30 young German-speaking mathematicians to enroll. It was a very difficult course, and by the time the course was finished, there were really only 3 graduates who they recruited. Their names were Marian Rejewski, Hendrik Zagalski, and Jerzy Orozitsky. And these 3 were the core of this team, and they are the ones who really made the early breakthroughs. They convened a conference at their secret headquarters. This was actually July 39, and at that conference, they gave the British everything. They revealed what they had done. They gave them a replica Enigma machine and all of their work. That information came back to Bletchley Park, and once they were established in Bletchley Park, they then used the Polish method to break the Enigma machine. The Poles had actually built some machines themselves, one of which was called a BOMBA. That machine, the name apparently comes from a Polish ice cream dessert of the same name. It's in effect vanilla ice cream with chocolate sauce around it.
This machine was called BOMBE in honour of what the Poles did. But the Poles' technique was based on the particular way that at that time the Germans enciphered their message headers. They, at that point, were repeating the message header, and that was the attack which the Poles developed on it. They believed correctly that when the war would start, that the Germans would change the way they were doing that, and they called for help. They told Turing and the people here everything they'd done, which we are and should be very grateful, but they also proved that it was possible. And that, I think, was the spur that kicked the Brits into actually doing something about it. Now, Turing understood the weaknesses of the way they'd done it and developed a crib-based mechanism based on the fact that every military organisation in the world cannot stop itself sending stereotyped messages. He then talked to a brilliant team of engineers led by Doc Keane, who told him roughly the speed that it would be possible to examine potential stops for. So between them, they then designed the machine called BOMBE, which would look for that and do so in a sensible time. Here is an example where we have intercepted this message SNMKG. We're pretty sure that that is, because this particular operator always did this, this is his morning weather forecast. So here we have the guessed German plain text, Wetter Vorhersage, weather forecast. And the two are lined up. At that point, the Enigma's ability or inability to encode letters itself is useful because you can make sure you've got no clashes here. And from these guessed letters, the crib makers would derive a picture like this called a menu, where you'll notice that at position ZZE here, G is encoded as E, so we have G going to E. At ZZP at the end here, E goes to V. This is reversible, of course. We can describe this either way up. So here's E to V. At ZZG here, S is going to A. Sorry, S is going to V, excuse me. So here's another link. And eventually we can go all the way around and we can close this loop like that. It was the closed loops that they were looking for. The operation of the BOMBE was simply that if there is a letter which you can feed in at this point, and which comes round through a string of 1, 2, 3, 4, 5, 6 enigmas, and comes back as that same letter, then it's possible that the position of these wheels match the position of the wheels when Gunther started encoding his message on his enigma. It turned out to be a bit more picky about loops and menus than perhaps they had hoped, although it worked. And at that point, Welchman added a completely left-field masterstroke called the diagonal board, which I think it is fair to say made the difference between success and failure to Turing's original idea. And here are my 3 diagonal boards. That's one, that's the other, this is the third one, cunningly placed where you can't see it. But can you see Z down to A? Okay. There's nothing connecting that to the machine. It's just bolted there for convenience. The only connections to the machine are when you connect X into one of the enigmas, as it were. What will happen is when we turn the machine on, you'll see it will run up to speed. Okay. The motor will be running and the clutch will drop in. Then you'll see the various carry mechanisms happening. Then when we stop the machine, you'll see it slow down, and then the clutch drops out. So, Tony, if you'd run it up for us, please. Okay. Would you turn on carry home? Okay. So what you saw there was the middle carry, then we switched on carry home to make the slow carry work all the time. So these bars are just pushing around all the drums. And you can see that all the 36 enigmas are just in step. They're all just turning and they are a resource. These are the very fast relays, the 3 banks, actually 4, for the chains that do the detection here. This is the control logic. Okay, and then this is the 26-bit register that notes a stop and then allows the machine to slow down before it stops for real. Our favourite statistic is the sheer amount of wire in the thing. We've lost count, but it's somewhere between 10 and 12 miles of wire in each one of these.
Germans really, there was 2 main systems they were using. Enigma was their operational system. That was being used for specific operational communications. Again, very short, maximum of 250 characters. Instructions, orders for a panzer division to move from one location to another, orders for a submarine to attack a convoy, for aircraft during the Battle of Britain to attack specific targets. The Germans started to introduce, through probably 1941, a different system. The intercept service, which Britain had put into place to intercept these messages, started hearing traffic, which was clearly not Enigma traffic. Enigma traffic was Morse code, easily identifiable. People can be trained fairly simply to transcribe, to listen to Morse code and transcribe the letters. This was a totally different signal. It was not discernible, it was not transcribable. This was Adolf Hitler's communication channel to his army generals. So very long-winded communications, top secret, and so this was an even more daunting task, arguably, than Enigma, because this encryption machine that was used with this system, there were various ones of them. Hitler referred to these as his Geheimschreibers, his secret writers. Several companies, Siemens, that exists today, were making a machine, Hagelin, but there was also the Lorentz company, and that was the primary machine, particularly Lorentz at SZ42. That machine, and unlike Enigma that had 3 encryption wheels, had 12 encryption wheels. They approached the post office research lab at Dollis Hill in London. A young engineer called Tommy Flowers got into the project. He was in effect told, well, go ahead if you can get approval. Flowers went back to the post office, got approval, put a small core team together, and in less than a year had a working prototype. Quite a remarkable achievement. The first Colossus, as this machine became known, the Mark I, had 1,500 valves or vacuum tubes in it. They brought it to Bletchley Park. It worked almost straight away. The people here were convinced. They asked for a more powerful computer. Flowers already had anticipated this. He already had it in production. 2,500 valves in an era when no machine had more than, that used valves had more than about 15. Here was a machine with 2,500. Flowers was told that they needed the Mark II by June 1st, 1944, because there was a certain date in the diary. June 5th, 1944 was a scheduled day for Operation Overlord, D-Day. It actually ended up being June 6th because of bad weather. Flowers delivered the first Mark II to Bletchley Park on June 1st. They switched it on. It worked straight away. They immediately started decrypting messages between the German High Command, and much to their delight, they discovered that all of the subterfuge about the D-Day landings had worked. Hitler had believed that the main invasion was going to be at the Pot of Calais, not at Normandy. That intelligence was fed back to General Eisenhower at Allied Supreme Command headquarters, and there is reasonable evidence to conclude that D-Day might well not have gone ahead on June 6, 1944 without the intelligence from Bletchley Park.
This is the Colossus computer at Bletchley Park. Now we're in Hut 4 at Bletchley Park, which was one of the first purpose-built computer centres, and some 10 of these machines were installed here starting in January 1944. Now, in the years previously, a new way of encrypting messages was discovered that was being used in Germany, and it was those high-level messages between Hitler and his generals, and they were encrypted on a machine called a Lorentz machine, and it used teleprinter codes to actually transmit those messages. Now, by 43, it was taking some 6 weeks to actually decode those messages, and decode those messages laboriously by hand. The problem with that is, within 6 weeks, the usefulness of the intelligence that you gain from those messages is obviously gone. So that process needed to be speeded up. Now, some techniques have been tried. Some semi-electronic techniques have been tried here at Bletchley Park. But this machine, when it was put into use in early 44, reduced that 6-week period to decode the message down to 6 hours. And that's really just a phenomenal jump. The machines, the
messages themselves were received at various intercept stations around the country and were punched onto paper tape. Now, there are two paper tapes on the machine here at the moment, one that we're running and one which is ready for the next run. Now, this tape, there are two here, if I take one, each row across the tape are punched 5 holes, and each of those is an alphanumeric character, and that's the encrypted message that was received and has been punched onto tape. Now, although Colossus has really all the elements of a modern electronic computer, it doesn't have the memory that we expect in a stored program computer. So what happens is that tape of that message, some 5,000 characters of that message, is actually formed in a loop and is read over here with a series of photoelectric sensors and lights, and each character is read, and the 5,000 characters a second are read. Now, each clunk of the machine we can hear there is another 5,000 characters being read into the machine. So we're reading that same 5,000 characters each time. This is the control panel of the Colossus computer. So it's this side of the machine that we would actually be, the Wrens in the wartime would actually be using. Now I can set up the particular algorithm I want to test and routines I want to test using these control panels. And each clunk of the machine at the moment is another state where we're actually trying a new algorithm and repeating that algorithm on that repeating 5,000 characters. The results that the machine detects are presented here. Now we're doing a statistical analysis of that encrypted tape. Now the machine was run for some 6 hours. There are 2,500 valves in this machine. You can't see that many from the front, but once we go between the axes of the machines, you get an idea of the scale. 2,500 valves. Each valve has a heater, a hot wire heater in the centre of the valve, and operates at about 200-300 volts DC. Now 2,500 valves plus the power supplies generates over 8 kilowatts uses over 8 kilowatts of electricity. And by this point, when we're standing in between the racks, you can feel the heat coming off of these racks. Colossus is a combination of electronics, and we can see the electronics here in these valve chassis members, and also electromechanical switchgear. So there are backs of relay panels here. These big single motion detectors are a sort of motorized switch that will actually spin around. There's banks of those in the machine. The technology is equipment that was well known for the British Post Office. This machine was designed by a chap called Tommy Flowers, and Tommy Flowers was an engineer at the research centre in London for the British Post Office. Tommy was asked to look at the problem of how to automate this task, this manual task. And Tommy came up with the idea of using electronics to do this. At the time, the idea of using more than half a dozen valves in any circuit was just simply poo-pooed. Valves had a bad reputation. People had valves in their radios at home. They failed when they switched the radios on. So the idea of using 2,500 was just simply phenomenal. But Tommy understood that it's almost certainly the thermal shock that kills valves in the first place. So if you leave the machine on and don't subject it to that shock, you won't have a problem. Now, all the 10 Colossus machines here at Bletchley Park were left on permanently. The machines were operated by Wrens in 3 shifts throughout the day. We have to be equally careful. This is a replica of the machine itself, but the same problems apply. We need to be careful in bringing the supply voltages up gradually so we don't suffer from thermal shock, and in the same way shutting the machine down. Tommy had the idea of generating the key, because it's a key that we're comparing with that encrypted tape, generating that key electronically. And these counters here, they're called the thyrotron rings, they're thyrotron valves, actually hold that, that count. Now, we describe Colossus as not having a memory. We say not having a memory in the sense that modern computers have a memory that's common for data and for programs. Well, the program here is set on those control panels at the front, and that's switch and plug programmed, much like, say, its contemporary ENIAC machine. But these machines, these valves at the back, do act as a store in the sense of counters, and they're actually counting the score that we're actually getting each pass through the algorithm. We can see at the back here, well, certainly some of the modern technology. I suspect the wartime guys that were building and debugging these machines would have given anything for a reliable oscilloscope, and let alone a logic analyzer. But if I look into the machine down here at the back, you can see the projected image that's coming off the tape, and that's shining onto 5 photosensitive valves. And it's those valves that are actually reading the 5,000 characters every second. And paper tape was used well into the 1960s and 70s. At this speed was simply phenomenal and hadn't really been thought of before. And our original museum director, Tony Sale, wanted to rebuild the Colossus and build a replica of the Colossus machine. And this was some 20 years ago. There's very little information out there. There are a few pictures that were kept, possibly illegally, a few scraps of circuit diagrams, and just the memories of some of the original pioneers who worked on the machine. And when Tony started the plan, Tommy Flowers was still alive and remembered and was able to draw circuits. But of course, finding the parts as well. But the important thing is the machine was designed by a post office engineer at the time, an engineer that was used to designing systems for telephone switching. So a lot of the components here, everything from the relay banks to the switches to the power supplies, were common to British post offices in the pre-war period. So when Tony then wants to find the components to rebuild the replica, he's lucky in the sense that the last of those exchanges are being decommissioned from post offices around the country. Tony was therefore able to really sort of back up a pickup truck at the back of the exchange and take away all of those components and dismantle all of those components. And they were absolutely perfect, and it was just that timing really couldn't have been better.
So Alan Turing actually left Bletchley Park after about 3.5 years. His involvement really finished. He went to the United States. Turing was not actually involved in the development of Colossus. Some of the statistical work that he did was used by the people, predominantly Bill Tutt, who's the guy that actually reconstructed the Lorentz machine, quite remarkably, a remarkable feat indeed. Turing got involved in things like speech scrambling systems and went to the United States and was involved in other projects, so he wasn't really involved in Colossus. At the end of the war, Turing went to work for the National Physics Laboratory, again pursuing these sort of ideas, and then of course he ended up at the University of Manchester, where Max Newman, who had run the department where the Colossus computers had been located at Bletchley Park, also ended up as the head of mathematics, and obviously then at that point Turing became involved in the very early computer developments in Britain. Gordon Welchman immigrated to the United States at the end of the war. In 1948 he immigrated to the United States and became involved in many of the early American computing developments. Project Whirlwind, Welchman worked at MIT, taught the first course in computing science at MIT. So Turing then was involved in things like the Manchester Baby and the Ferranti Mark I and the early computing developments. I guess this is well known, of course, Turing tragically committed suicide in 1954.